Now, it is my pleasure to introduce Dr. Chris Turman of MIT CSAIL to moderate our next session. Let's give the moderator and the speakers a warm welcome.
Good morning. Thank you. I've been an educator for many years, and I've suddenly realized that I'm entering probably the most exciting stage of my teaching career. In the next 10 years, education is going to change dramatically. How students learn and teachers teach will be considerably different in the year 2025 than it is even now here in 2014. One of the important parts of our job in a research university is to explore and think about how to introduce new tools to help computers do neat new things, and in this case, how they will impact education. We were fortunate enough to have some very inspirational conversations with Chairman Barry Lam at Quanta Corporation, and he has been sponsoring for the last couple of years a research program at the Computer Science and Artificial Intelligence Lab at MIT. And what I'd like to do today is to share with you some of the research efforts that we're doing, which you'll see touch on many different themes. So we're interested in how to make teachers teach better, how to engage students more effectively, and how they can learn better. We're interested in figuring out for the first time how to use almost a laboratory-like experience that these large, massive online courses provide. They give us real hard data on exactly what students are doing and exactly the moment at which they grasp the concept. And then we can look at that and figure out what it was that worked. And then we can use that to improve our teaching and to find learning paths for other students. So we have 4 different speakers today who will touch on different tools that can be useful in different phases of that process. Our first speaker is Professor Rob Miller. He leads our user interface design group. And one of the things that's interested Rob for a very long time, because he teaches our very large software engineering course where students generate a lot of material that needs to be reviewed by the staff. And we think about putting a course that requires a lot of staff involvement in student assessment up on the web. We realize that there's a scaling problem. And so Rob has been very interested in how to use the students in the course, alumni of the course, other people around the world to help ease the job of sort of looking at course material and giving students timely feedback. So Rob is going to talk to us about online education with learner sourcing.
Thank you, Chris. Maybe we can switch to the slides here. Great. What I'm going to talk about today, let me actually start by explaining the last word of my title, this idea of learner sourcing. And it really goes back to as Chris said, the scale of these courses. I've been teaching at MIT for over 10 years, and a large course at MIT is about 300 or 400 students. But a typical course on edX is 50,000 students. So we have the same size staff that we're trying to use to teach 3 orders of magnitude larger group of people. That's both a challenge, because the traditional ways that we teach on campus are not going to work with that kind of scale, but it's also actually an opportunity, because now we have actually a very large pool of people that we can take advantage of, the students themselves, to help us teach the course and to help us make it better. So this word learner sourcing is really an evolution of the term crowdsourcing, which has been popular in the last 5 years or so as a new way to extend the reach of an organization by taking advantage of a large group of people out on the web. And so an example of a site that makes that possible is Amazon's Mechanical Turk. It's basically a labor market that you can get small bits of work from many, many people to help do something that your organization is trying to do. And so that's been an active area of research and actually industry use over the past 5 years or so. And now that we're entering the age of online education, of massive online education, we're thinking about how we can use the tools of crowdsourcing when your crowd is a group of learners, is a group of students that are taking the course. So what they're doing is small bits of work that help make the course possible, help make the course better. And what they get in return is not getting paid small amounts of money, but instead it's hopefully learning something more, getting some more of their own educational benefit out of what they've done. So I'm going to show, and there are basically two ways that we're thinking about taking advantage of the large scale of learners in our course. One that we call active learner sourcing, where we are explicitly, directly asking students to do something that will improve the course. The other is passive learner sourcing, where students are simply doing the things that they do in the course, watching lectures, doing assignments, and we're watching what they're doing. We're collecting the data about their activity, about their behavior, and mining that data, trying to infer things from that data that will help us make the course better. So I'm going to show you 3 examples very quickly. I only have 20 minutes, so this will be a quick overview of each of these projects that illustrate both active learner sourcing and passive learner sourcing. The first example will actually not be in the context of a formal course, but instead will be about informal learning using how-to videos. There are lots of them on YouTube, and people are learning from them. So this will be somewhat outside of the edX kind of MOOC world, but it will still be relevant to online education. The second one will be in edX, so we'll be looking at how students use lecture videos in edX courses and how we might use that information about their usage to make the lecture videos better. And then the third is looking at solutions to problems that students are submitting and mining those solutions to learn more about the assignments and to give students better help. So let me dive into the first one, which is about how-to videos. So the web is full of learning material that has been informally created. So if you go on YouTube and do a search for example, how to apply makeup, you will find thousands and thousands of videos about makeup. Thousands of videos about cooking, thousands of videos about home repair. One domain that we've been looking at a lot because it's got a lot of videos up there is Photoshop. So Adobe Photoshop is an image processing program which is very popular but also very complex and hard to use. And there are many, many videos on YouTube that explain how to do interesting things with Photoshop. So this is an example of one of them that shows the Photoshop interface and shows a photograph that somebody is trying to make a change to, apply an effect to. One of the problems with YouTube as a learning tool is that it doesn't show you very much about what's happening inside this video. This is actually a step-by-step video that is showing you first you do this in the Photoshop interface, then you do that, then you do that. You can't see any of that structure from a standard video player interface. If you think about cooking, the recipe that the video is following is not visible in the YouTube interface. And that turns out to make it much harder to learn anything from it. In fact, we've developed a new video player. So you're seeing here a YouTube video up top that is a Photoshop tutorial. And what we're adding to the bottom is a timeline showing the steps that video goes through in order to produce this effect, particularly the actual tools in Photoshop that you would use if you followed this procedure, and also how the image that you're processing is changing over the course of those steps. So that idea, showing the steps and showing the work product, is the fundamental idea of this video player. And we've used this not just for Photoshop, but also for cooking. So imagine this being the things that you are doing, the ingredients that you are adding. And these are pictures of the food as you are cooking it, as the recipe is developing. We've done some lab experiments that show that people trying to learn how to do a process from a video learn much better and actually produce better results when they have this extra structure information than if they just see the usual YouTube video player. So this is valuable for learning, and we want to be able to add it. Now the challenge is there are already thousands of these videos up on YouTube. They don't have this information, or it's embedded in the video somehow. We need to be able to pull it out and display it to the user. And that's where we're taking advantage of people. So that's a very hard problem to do automatically. What we do instead is we ask the crowd to find that information in the video. We have them do a succession of small steps in order to start from a video already on YouTube and pull out those steps and the work product so that we can provide this better user interface. And I'll show you sort of quickly what those steps are that people in the crowd are doing. One of them is to watch a small segment of the video and type in the step that is being done at this point in the video so that we get those steps pulled out. So here, for example, they're applying color to the lip. And then another step asks other people watching the video to look at the steps that people have proposed and say which one of them is the best description of what actually happened here. This is like a voting part of our workflow. And then finally, we pull out frames from the video and ask another group of people which of these are the best pictures of what the face, in this case, looked like before the step and what the face looked like after the step. So we're asking human beings to choose those. And the result of that is this sort of rich representation of what's going on inside the video. And then the next step for this that we're looking at is to generalize, to abstract away from this particular set of steps in this procedure to the reasons why those steps were done. So what are the higher level goals of each of those parts of the procedure so that the learner who's watching this can start to really generalize and understand what's going on at each point. And again, these are things that we're going to ask other learners to produce and to verify. So that's an example, a sort of a very simple example of how we can take existing learning material on the web and improve it by using people, by using students. A second example, so that was active learner sourcing. We were asking people particular questions about this video. Now I'm going to show you an example of passive learner sourcing, where we're watching how students are interacting with lecture videos like these. So these are some frames from videos that have been used in edX courses. And we're going to collect data from the video players that these students are using to understand how they're watching these videos and use them to find moments in the videos that may represent important places or places where the video needs to be improved, where the student is confused or bored. So this particular data I'm going to talk about comes from 4 edX courses over a variety of disciplines. Total, there were 130,000 students that watched these videos, that participated in these courses. These are all fairly short videos, so they're on the order of, on average, 7 minutes long. So don't think about an hour-long lecture. These online courses try to have their video segments be very short. And a total of 40 million play and pause events. That's what we're looking at here. Places in the video where the students have pushed play or pushed pause. And by processing those play and pause events, we can see which parts of the video have been viewed more than other times, right? So these are peaks in the playing behavior. These are places in the video where more people than usual have played it. And frequently that's because students have had to come back and replay it, rewatch that part of the video. So that's what both of these peaks sort of show that. This is total number of play events at that point. This is the number of people that are rewatching that moment of the video. And then we're also looking for data at the video itself. In this case, a very simple statistic which just compares two adjacent frames to see how many pixels have changed, how much of the video has changed. So this very strong point here, 100% of the frame has changed. This was a cut. This was a cut probably from showing maybe a picture of the lecturer's face to showing a PowerPoint slide. And that's why during this part of the video there's virtually no change, because it's just, a slide that isn't changing like you're all looking at right now. So we're using these visual transitions as well to help try to explain why we're getting these peaks. What's going on? Why are people rewatching? And we can classify them into a number of types. So here's an example where a peak in watching follows a visual transition. So this is probably a place where students are coming back to start watching this section again, right? This is a place where the lecturer has moved on to a new part of the material. Seeing a peak like this might make us think that if we're going to revise the course material, maybe this would be a good place to actually chop the video into two smaller videos, right? So that it's easier for students to start from this point. Here's another kind of transition. It's one where the rewatching peak happens just before the visual transition. And one possible reason for this, and I've experienced this myself as a student in online classes, is that the video editing cut away too quickly from a complex slide here. This is showing a Python program that the lecturer has been explaining. Cut away too quickly to his face. I don't want to see his face. I'm still trying to understand that slide, right? So I have to back up in the video and look at that slide again. So this is actually a video editing error, right? It's one that perhaps we could even fix automatically by changing the way where this visual transition occurs. I'm going to jump over a couple of these other ones. There are also some places where we have no clear explanation from the visual part of the video to understand why there is a rewatching peak. And what some of the ongoing work that we're going to do is looking at the audio part of the video, the transcript, to see if we can understand why those rewatching peaks occur at places like that. But key question here is, how can we take advantage of this interaction data in order to improve students' experiences? And here's one prototype that we've been looking at. So now we're showing to the student a timeline of how other people have been watching this video, so that now the students can see where these peaks are. And furthermore, we can highlight places where our system has automatically detected a likely interesting place. And when there are transitions that have peaks of watching around them, we can pull out the frame that corresponds to that transition. And we found that for some videos, this actually gives a very good outline of what the video is actually going to be about. So we've passively discovered the sort of key moments in the video just by seeing how students are actually watching it. Okay, so that's two examples of learner sourcing, both in the video domain. The last example that I want to go through is looking at how we can use solutions that students are submitting. And these kinds of solutions are bigger than the ones that Anand Agrawal was showing as examples. These aren't just little formulas. These are solutions to design problems. So they might be circuit designs, they might be programs, Python programs, and in many of these open-ended design problems, you have multiple ways to answer the question. Two different circuits that both do the same thing. And as a teacher, I know that when I describe a problem to students, I often have only one answer that I can think of as being the most likely one. But then when I get answers back from students, suddenly lots of other possible solutions come up. So actually having the benefit of lots and lots of students giving answers actually increases what I know about this problem. So we want to be able to take solutions that students out there are submitting and cluster them. That is, find common kinds of correct answers. And these green ones are correct answers. We also might get wrong answers, things that don't satisfy the requirements that the problem stated. What do we want to do with them? Well, one thing we can do with them is use them for teaching. So if a student answers with a circuit that looks like that, we should probably show them, hey, there are other ways to do this. And can you look at these two circuits and talk about why one is better or one is worse, and what are the trade-offs between them? These are important questions for students to understand in engineering. When we see a wrong solution, how do we give hints to the student who made this wrong solution? How do we help direct them to the right solution? And can we make sure that we're directing them towards a solution that is close to what they were trying to do, rather than to a very different cluster that may require them to throw away everything they were already trying? And a key problem here from a computational point of view is, what features do we actually want to use for clustering solutions? So this is preliminary work, but I want to show you a couple of case studies that we've looked at that come out of MIT courses. One of them is from a digital design course, in which one problem was to create a Turing machine that could match parentheses, that could check a string of parentheses and see whether it was well balanced. And this was a case where most of the staff of the course thought there was only one sensible way to do it, which was to find each correctly matching pair, sort of from the inside out, and deal with those. So what you would end up with, if you graph the behavior of the Turing machine, it would kind of bounce back and forth like this as it matched associated pairs of parentheses. There is actually another correct way of doing it that the staff didn't even think of until it started cropping up in student solutions. And that is to simply find the first open parenthesis and match it with the first closed parenthesis, even though they may not actually be matching ones. You may have additional open parentheses in between. That actually still gives you the right answer, has a very different behavior, and actually runs faster. So when you mine the solutions and you use the right kind of visualization to show it, those differences pop out. A second example that we've been looking at is answers to a MATLAB programming game that has a large number of players out on the web. And I've been told that time is up, so I'll quickly just say that what this visualization is showing is that there are two kind of common solutions to this, where if you graph the MATLAB programs by size, they will sort of pop out as sort of separate green rails there. So the goal for this is to try to learn from these multiple solutions and help improve the way that we give feedback to students. So I've shown you three examples of how we can use the learners in a course in order to try to improve the experience of the course. I think this is one of the ways that we can take advantage of what otherwise is a real problem in massive online courses, the fact that they are so very large. And I'd love to talk to anybody who is interested in this during one of the breaks. I should stop there.
One of the tasks we have as teachers is to help our students learn better, and we often watch them work the problems. We work with them, and we can tell by the way what steps they do and the order that they do them, what they're thinking and how we might help them do better. Well, when students do courses online, we don't get to watch them, but we do get to collect a massive amount of information from their interactions through their browser with the course material. And it's analyzing that information that gives us the possibility now of using the MOOCs as laboratories to figure out how students are working with the material and how we can make the material better and how we can help the student perhaps make a good choice about what to do next. And that requires basically looking at this massive amount of data, billions of click logs, and then analyzing them for patterns and relationships. Our next speaker is Dr. Uname O'Reilly, who's going to talk. She's the head of our AnyScale Learning for All, which is a research group at MIT CSAIL, which is devoted to big data and machine learning. And she's going to talk about how she likes the work she's doing on knowledge mining of online learning data.
So you're hearing about MOOCs today, and I'm going to tell you about how we can knowledge mine MOOCs and conduct analytics of MOOC behavioral data so that students can potentially benefit from those insights, and teachers can benefit as well, and we can figure out effective practices for MOOCs. One of the unique features of MOOCs is the flexibility they give a student. So in a normal brick and mortar class, students have very little flexibility. They all have to collectively converge on the lecture, and they have to sit there and listen to the lecture at that exact time. And they don't get to play it twice. They sleep in, they miss it. And this repeats on and on. But in contrast, students in MOOCs follow a very unique educational pathway. And let me explain that. A MOOC, the sequence of material can be arranged in a sequence of modules. And there's only synchronization points for students at the end of each module with something like a problem set or an exam. That means that a student can very independently and flexibly negotiate every piece of every interaction they have with content up to that synchronization point. So that means a student can log into the edX website at any time of day, and they can decide where they're going to start to learn. They can pick up the video, they can watch it for as long as their interest holds, or until they think they've mastered a concept. They can return back and forth across that video, maybe cross-reference a video to a textbook. And then when they've decided they have mastered a concept, they can try a problem. And immediately, as you've seen demonstrated in the first talk today, they will get feedback on how well they're doing. And they now react to that feedback. They can go on if they were correct, but if they're incorrect, they can choose where they go and consult material in order to clear up their error in thinking and attempt the problem again. And really what MOOC analytics is about is understanding how students behave when they interact with this massive online open course. And this is quite a different set of data that we're going to analyze from what you would typically analyze if you were an educator and an education researcher who was looking at students in the normal brick and mortar classroom. So in the brick and mortar classroom, to actually observe students, you have to stand back and watch them all, and you don't get a very focused view of any of them. If you choose to focus, you zoom in on one, right? And if you need to know more information, you might have to intervene and interrupt. You actually interact and change the learning experience simply by being an observer and a researcher. Well, all this is put aside when students now are examined through their behavioral traces in MOOCs. What happens is that a student is tracked very similar to the way that you're tracked when you go and shop on an online internet site. So when you arrive at the landing page for your favorite store, right, your move to that location in the internet is recorded. And that online store's platform, which delivers the commerce for you and the shopping ability for you, now collects every keystroke you made and the time at which you make it, right? And it collects every mouse button click as well. So all this tracking log is actually collected from you when you shop. Well, the same thing happens with a MOOC platform. When a MOOC is released on a platform, the platform provider actually manages in a software layer to collect that entire clickstream of data for every student. It's stored very disorganized all over the internet because it's very, very big. And that clickstream data is complemented by the other data that can be collected about students. The data that's given to them, given to the platform provider and the content provider when the student registers. The forum data, which shows students discussing course content, and all the answers that students actually give to problems. So we have this wide array of data distributed over the internet. And if it can be wrestled and wrangled and brought into an organized state, then what we're going to be able to do is answer some very interesting questions. And let me just show you some examples of those questions. Some of the questions that you might want to know about a MOOC are descriptive in nature. What countries do students come from? How many students speak the language I'm teaching in? Right? There's another question, which is when are students actually doing the work? When are they logging in? When are they looking at my content? How does that behavior correlate with when there's a due date on the assignment? And if I asked you this about one class and I showed you the answer, would you be able to tell me that the same thing with same pattern of event timing would happen on another course? Perhaps even another course with a totally different platform provider and a different means of looking at the data. Well, that's the sort of question we want analytics to answer. I'm actually going to show you the answer to that question later. Okay. There's some questions that also require a little bit more extensive knowledge mining and more advanced machine learning analytics. And part of that comes from there just being a lot of data. But the other thing is that we really would like to mine the data to find patterns of behavior. Because then we can correlate patterns of behavior in terms of what content students are looking at and the type of resource they're consulting and their actual answers to questions. We can correlate that with their achievement, whether they got an A, whether they got a B, or whether they got a C. We might correlate that with the country they come from or their mother tongue. We might go into another level and actually use an unsupervised learning technique and see if the patterns just emerge and see if that might explain something like a learning strategy that students are using to navigate the MOOC content. And there, if we can correlate that to achievement again, we'll understand successful strategies and we'll be able to foresee an unsuccessful strategy unfolding. So perhaps we can intervene. I talked to instructors and asked them what they wanted to know. And I think two important questions came up. We see a lot of attrition in MOOCs. I'm going to show you results from the 600, analyses from the 6002X first offering that was presented to you by Anant on the first talk. And 50% of the students dropped out in that course each week. While still a tremendous amount graduated, we want to know why students are dropping out. Maybe it's okay. But if there's students who are in there and they're just reaching a crunch point on the material, it would be nice if we could go back to the history of former students who stayed in and former students who dropped out, compare the patterns and recognize the students who are at risk and make an intervention. Another good question is to confirm the assumptions professors make about the content. So an instructor may have a priori assumptions that this concept's difficult for students and this concept's hard. But we can go to the data and we can actually look at how many times that question about that content was answered correctly the first time. And on average, how many attempts the students tried before they got that concept right. And that data is now quantitatively either confirming or denying some assumption or hypothesis instructors had before. So it's very powerful in that way. Now, in effect, there are thousands of experiments in MOOC teaching going on right now. That's because we have multiple platforms that allow universities and other content providers to run MOOCs. And each of those content providers may be running multiple MOOCs. If we want to do data analytics at scale, I think there's a very interesting set of questions that arises from being able to compare the behavior of students on one course to another. And for example of that is, say I wanted to look at the behavior of all students trying to learn their first course in computer programming. The questions and the answers there should be agnostic to the platform that this course was offered on. But the challenge in data analytics is that the data being saved by these platforms, which gives us the behavioral picture, is actually in different formats. So that has to be solved first. Another problem that has to be resolved is the fact that the platform providers run a course, and they actually archive the data or warehouse the data in the internet. But when the course is completed, in the edX case, the data is consolidated and then passed back to the university who actually provided the content for the course. Now what happens is that gets done time and time again for each university course, but I've created silos for the data. I now have data for one university in one place, and there's a wall, because of privacy requirements, which precludes analysis from being done on data at another university, unless data analytics can come up with a solution to that. So for those two problems I just told you about, the fact that there's isolated control of the data, but we'd like to have general access, and the case where we'd like to be able to analyze data from any MOOC and cross-compare regardless of what platform it came from, what my group has done is to recommend a common data format for all MOOC data. And it's called MOOCDB, and I don't want to show you the innards. What I want to tell you is that what MOOCDB does is perform a translation on each platform's data into a common format. And what that implies is that now we are comparing apples to apples because the data is organized in the same way very efficiently. And once you have data from different platforms in the same format, all sorts of good things become possible to leverage analytics capability. And there's a few issues that have to be addressed if you're going to do massive analytics at this scale. One is you need algorithms that run on big data. The second is that you should make sure that no software that's being written to analyze this data is written twice. The software needs to be shared. We need to have a common, open community of software sharing so that we can leverage each other's work. Now, what's going to enable that is the common data schema. Because when there is a common data schema, the software written for that, under the assumption of that schema, can be transferred into someone else's hand and be run on their data. And that's a very powerful but simple notion, which is going to allow us to share analytics. And that's what MOOCDB addresses. I have another platform on top of MOOCDB called MOOCViz. MOOCViz is the facility for sharing that software. It also provides one other important thing for data analytics in MOOCs. What it provides is a capacity for putting many eyes on the data. Because data analytics is just not going to be powerful enough unless we bring it to every stakeholder's eyes. And not all the stakeholders are the ones who are conducting the analytics, the technologists like me, or even commissioning the analytics. So what we need is a community of engagement, intellectual engagement around the results we're getting from all these simultaneous experiments. And the MOOCViz platform is a way of sharing the data and sharing the results and building a conversation around the results so that we can build upon that and decide where we go forward in changing MOOCs. So MOOC data science really involves taking the data from ingest into an analysis platform all the way through to visualization. And what you see are these two projects are necessary to, one, get the data to a common format, and two, to actually bring the analytics and the results of the analytics into alignment so that many people can share them and a whole community can work together on them. So now I'm just going to demonstrate an example of analytics which brings out how we've addressed or brings out the challenges and resolves them that I've talked about earlier. So what I have here is a description of two different courses. They're not particularly similar. You might not necessarily want to compare them, but I'm using it for demonstration processes. One is a course given at MIT, through MIT on the edX platform, 6002X. It's on your right-hand side. And the other is a course given at Stanford on the Coursera platform. Now, we had seen analyses of these independently, but now I'm going to show you analyses side by side because of what happened through the enabling of MOOCDB and MOOCViz. My group took the 6002X data and we reformatted it, decreased its size by more efficient storage with our data model, and we created a database of the 6002X data according to the data model. We then wrote visualization software that gave us the scripts, the visualizations you're going to see. Stanford got in touch. They heard about the MOOCDB model. They said, we have a course. We'll figure out how to conform to your data model. And you know what? It needs some tweaks because it was the only first time we did it. So we extended the data model to account for the fact that there are slight platform differences. And Stanford converted their data to their data for Crypto 1 to MOOCDB format. Overnight, we passed them the scripts and they ran all the analytics. And that's extremely powerful, despite being quite simple. So let me show you the first result we got. Side by side, what we've done is we've had a script, and that script calculated the enrollment per country. And we looked at the relative number of students in a country who gained a certificate. And what you can see here is that for a circuits and electronics course, it's most popular in Western Europe, and it's the countries like Greece and Spain where we see very high completion rates. In contrast, in the crypto course, the interest in the crypto course is in Asia, right? Russia and China, and all those guys are getting their certificates, right? So that might be content, it might be other things, but we have that basis of comparison. Now, the other question I raised earlier was, when are students using the course? And do you think that the pattern of student usage is going to actually repeat itself across courses? So we've got these two courses, and they're actually different lengths in time, they're on different subjects, they actually have different students from different countries taking them. We're going to normalize actually, when they're actually to their local time. But let's take a look at the event timeline for both of those courses. It kind of looks the same because they all have these peaks. So what you see up top is a timeline on the x-axis and the amount of events of people actually engaging the course. And you see these spikes. Those are actually, the 24-hour period before the problem sets due. And if you look down on the Crypto 1, you see those same spikes. And guess what? They're occurring relatively at the same time, 24 hours before those problem sets are due. So it doesn't matter what the students are studying or where they're from. They all have the problem of trying to cram in the work before the deadline. And that's confirmed by the data. So I'm going to show you next a picture of what resources students are using to learn. And I'm going to subdivide that analysis of what resources they're using by what country they come from or what grade they got. So the first thing we did was we took all the different content on the website and we classified it into a resource type. And of course, the most common resource or the most obvious resource is the lectures. They were on both platforms provided with videos. But then we bundled up other content into things like tutorials and information in the edX case and into wikis and forums in the Coursera case. And collectively, amongst Stanford and MIT, we're now working together to build this visualization. Even though we had our data in different places, and I never looked at their data and they never looked at my data. Right? And what you see on the top left there is the relative resource usage of each student subdivided by what grade that student got. And what we see is that if you squint a bit, because I understand that my graphics are a bit rough, you see that A students actually use the lecture material more than B students and C students. And it is not quite as consistent in the Coursera or the Crypto 1 case, if you look in the upper right. It also becomes interesting when you look at country data. So if you look at the lower row here, the 6002X data, we had to ignore the Chinese data. That's because YouTube was the delivery point for the videos in this first offering, and it was not consistent whether students were going to use the YouTube video, we would get the clickstream data, or whether they were looking at the video offline. So ignoring the Chinese bar, what we see is the Indians are actually looking at the lecture a lot less than any other country. And you know what? When we move over to the crypto course, you see the same thing. And it's actually a very marked difference here. So that now the analytics has raised further questions that we have to go and investigate. I'll just say one more thing about the analytics is that it's really important when one builds these frameworks for sharing software to get the structure in place. And we put some structure in place so it's easy for analytics to be developed and then shared, and the results like this to be put on the web so other people can look at them. And we also provide statistical analysis within these scripts so that you can actually do statistical comparisons and actually get more robust and rigorous research results here. So let me conclude with a takeaway message, set of takeaway messages. If you only remember one thing from me at my talk today, I'd like you to remember that online and MOOC education offers a new way to study learning and to improve online teaching when we invest in data analytics and apply it across courses and platforms. But after that, if you can remember still more, I'd like you to remember that the evidence we're gathering is very different between a MOOC and a brick and mortar course. And yet we can resolve all of our challenges and conduct many experiments on all MOOCs. And we're going to get great insights from being able to do that very scaled up analysis beyond that of a single course. So with that, I'll leave and just acknowledge the large team and the very generous support of Project Cumulus with Quanta. Thank you.
One of the exciting things you can do as a teacher is say, okay, I'm going to suddenly stand up and teach in front of 500,000 students. That's great. How am I going to present my material online? And there's sort of two choices. One is to prepare PowerPoint slides and put a voice narration over them. And if you've ever made any attempt to watch hours of narrated PowerPoint slides, you realize that they are sort of, shall I say it, boring. I mean, they're hard to watch. Much more exciting, and you see this used by the more innovative teaching websites, is to use handwritten slides. And to actually watch the handwriting as the professor explains and writes at the same time. And if that's of course very much what we're used to as teachers who are writing on the blackboard and talking as we go. It turns out that handwritten slides are very hard to produce with current tools, and this was a problem faced by Professor Fredo Durant as he was preparing some of his own online material. He, however, has the advantage of having a lot of experience in graphics. He's one of the leaders of our graphics group here at the Computer Science Lab. And he has the ability to write his own authoring tool, which he's going to explain to us now. So authoring tablet video lectures with Pentimento, Professor Durant.
Thank you. I think we all agree that the goal of the digital revolution in education is to make high-quality education available to everyone. And today I want to talk about half of this story, which is to make high-quality education. And unfortunately, authoring educational content is hard, which is too bad because I think that the promise of online education is to enable as many teachers as possible to create good educational content, and hopefully the best content will bubble up and everyone in the world will have access to this high-quality content. And another aspect of education is that you always want to refine your content. Every year you try to make your lectures better, and I think that online this should be true as well. I should be able to take my video lecture from last year and make it a little bit better based on analytics like Uname presented or direct student feedback. And unfortunately for videos, authoring and editing content is really hard, and current tools are very inadequate. I will talk today about tablet video lectures, a very popular style for online education. The Khan Academy is one of the famous ones, but you have many others. And in this style, you see the handwriting and the hand-drawn diagram of the professor while you hear the explanation. And I don't know if some of you have tried to produce some of these, but it's really, really hard. I tried and I failed miserably at first. Because the problem is that currently, the only option you have is to use screen capture. So you open a drawing program, you start recording, and you speak and you draw at the same time. And you have no possibility of editing after the fact. So that means you really need to write everything correctly, you need to say everything correctly, and you need to do both at the same time, which is really, really hard. And so, in general, the problem with current approaches is that they're very rigid, and you need to get everything right in the first place. You can't correct mistakes, you can't add content, and space is actually a big problem. That's the one that killed me the first time I tried to make a lecture. I started doing a diagram that was too big, and I didn't have enough space to finish my diagram. And in general, I feel this is pretty similar to writing text on a typewriter. Typewriters used to be great a long time ago, but they're very rigid. You type your text, and then if you want to edit it, pretty much you start typing the same page all over again. And this is currently the situation with the authoring of video lectures online. And if you look at the way we edit text, it's a lot more flexible today. Every single word processor allows you to correct your mistakes, to insert text, in the middle, and to really iteratively write text, and to write text in an order that doesn't have to be the order in which people will read it. And we really need this kind of flexibility for the authoring of video educational content. And this is why I've been developing a tool, which I call Pentimento, which seeks to address these problems. So, let me show you.
We present Pentimento, which enables the non-sequential authoring of handwritten video lectures. Pentimento relies on a new, sparse, and structured representation that builds on space-time strokes and adds discrete temporal events for dynamic effects, such as color changes or basic animation. We also decouple audio and visual time and use a simple retiming structure based on discrete correspondences interpolated linearly. This makes it easy to maintain and edit synchronization. Let's look at an authoring session with Pentimento. We can record strokes over time with the standard pen interface. The lecture area is the white rectangle in the center. If we run out of space, we can keep writing in the red safety margin, stop recording, and edit the layout using a familiar vector graphics interface. However, our edits are retroactive and affect the stroke from its inception. The lecture's temporal flow is preserved, and the equation looks as if it was written with the correct size in the first place. We continue our derivation, but we decide that we went too fast and that an extra step might help students. We move this equation down to make room for the new step, using another retroactive edit. We move the time slider back to where we want to insert the new content. We press record and add the new line. We perform more layout refinement and complete our demonstration. In this scenario, we have focused on visuals first, and we now move on to recording the audio. We first make the audio and visual timelines visible. We proceed piece by piece and select in the visuals the part that we want to narrate. We press the audio recording button and say our text. The audio gets automatically synchronized with the selected visuals. We proceed to other visuals and record the corresponding audio. We can also select in the audio timeline and record. Our approach relies on discrete synchronization constraints between the audio and visual time, which are visualized as red ellipses in the audio timeline. We can add constraints by selecting the visuals, moving the time slider to the audio time where the appropriate narration occurs, and using the timing menu or a keyboard shortcut. Here we set the end of these visuals to occur when this audio is heard. We can also drag constraints to change the audio time or the visual time, and the visual timeline and the main view reflect the change. We can also delete silence, and the visuals get sped up automatically. Once we have recorded the audio, we realize that the derivation could be clearer if we replace the mean mu by e of x. We first make space for the change. We select the strokes we want to replace and press the redraw button. We write e of x, and the timing of the new content automatically conforms to the old one and preserves audio synchronization. We also realize that some of the narration doesn't have corresponding illustrations. We make space and use draw to add visuals without affecting the audio. We derive a fundamental identity for variance. Variance is usually written sigma square. It is defined as the expectation of the square difference between x and its expectation. We can distribute the square, which gives us the expectation of x squared minus 2x e of x plus e of x squared. We get e of x squared minus 2 e of x plus e of x squared. We clean up this e of x and get e of x squared minus 2 e of x squared plus e of x squared. We now cancel one of the two negative e of x squared with the positive e of x squared, and we get the final equation. Variance is equal to e of x squared minus e of x squared.
All right, so let me try to show you in a little slower manner how it works. So I apologize for the handwriting. I'm not used to write standing, holding my tablet. Whoops, and I'm getting in trouble with Victor's computer. So I can start recording. I think I'm going to be in trouble because of the touch. Here, and now everything I say and write is going to be recorded, so I can start a derivation. So for example, ax equal b, and then maybe I say x equal b over a. So I stop recording. So I should have my audio here. This is my little lecture. I can go back in time, check what was going on. Yep, here we go. All right, so let's go to the end. And maybe I decide that I want to add some content in the middle. So I first make some space, move stuff around. So again, everything in the past is modified. And then I go to the point where I want to insert my new content, and I press record again, and I can say something like maybe 1 over AX is equal to 1 over AB. And note how now it looks like I had recorded this content in the middle in the proper timing. And so in general, this kind of flexibility makes it a lot easier to create online videos and modify them and improve them over time. All right. So in general, Pentimento supports strokes, which you can use for writing or for making diagram. It allows you to edit audio, remove silences, trim things, re-record the audio if you're not happy with it. You can use background slides if you want, which is very important to a lot of people because they already have a lot of PowerPoint content. And it has basic animations. You can move the strokes around. And for example, you can do things like take the left-hand side of an equation and move it to the right-hand side for more visual demonstration. And essentially, you can think about Pentimento in terms of its two main windows. The first window is kind of your drawing program, your PowerPoint, where you do all the visuals. And there's a second window that's more like a video editing application like Adobe Premiere or Final Cut Pro, but that's more specialized for educational content, and that's a lot easier to use than this software. And the key to Pentimento is the kind of edit that you can do back in time. And we've identified 4 types of edits that are important that deal with the layout of the image, with the ability to redraw strokes. So I guess I could demonstrate this because I found it very helpful. So for example, I can select one of my strokes where maybe, my handwriting was not very good because I'm standing here, and I can hit the redraw button here and redraw a nice B. That's not a much better B, but oh well. And now this looks like I had drawn this B in my lecture, and importantly, the timing is respected. So the synchronization between the audio and the visuals is respected. And this is even good for people like me who have a bad handwriting. In some lectures, I actually asked a student to rewrite everything I had written, and I didn't have to worry about synchronization because Pentimento preserved it. Oops, and now my slides are gone for some reason. Yep, sorry. I have to learn to use Victor's computer. As you saw, you can insert content in the middle of the lecture, and one other thing I haven't demonstrated is that you can change the order of things. Because it happens very often, especially if you start by recording the visuals first and then do the audio, that you just draw without worrying too much about the order of the lecture. And very often you might want to change the order. For example, write the equation first and then do the diagram, and then you decide, oh, maybe the diagram first was a better idea. So these 4 types of edits are very important to make the authoring non-sequential and flexible. And the other big thing with Pentimento is this very flexible retiming between the audio and visuals. You can say, I want this part of the audio to correspond to this visual, which makes it very easy to synchronize and very easy to decouple the recording of the audio and the visuals. Because you can just say the audio, not worry about the timing and how it's synchronized with the visuals, and then later put some synchronization and say, this word in the audio should be said while I was drawing this stroke. And these features are actually very useful for translations because it means I can change my handwriting, my visuals, to a different language just by using redraw and then write the thing in your new language. And vice versa, you can very easily change the audio even if the other language takes longer for one sentence or shorter for another one. Because the synchronization is so flexible, you don't have to worry about it. You just change your synchronization constraints.
Ray tracing is a fundamental.
I'll skip the sound. This is actually the video lecture that motivated me to do this. It has a pretty complex diagram and layout. When I tried to do it with traditional approaches, I just couldn't do it. I wasn't planning my space well enough. It explains a very classical computer graphics technique. Pentimento is still a prototype. It's not distributed yet, but we've created a number of lectures with it on a variety of topics, from basic math. We have something on barcodes. We have something about geography. One thing that's really cool is that you can put an image as a background and trace a map over it, and then you remove the image so the students think that you're really good at drawing a map of the world. I love this kind of stuff. And another thing that's exciting is that the content is mostly strokes over time plus audio, and so you don't really need to encode it into a video. You can just send the strokes directly, which is a lot cheaper than a big H.264 video. It also looks better and sharper. It's independent of resolution. And it also enables a number of pretty exciting navigations. In our web player, you can click on a stroke, and it moves the video back in time to when that stroke was drawn. So if you wonder, oh, what was he saying about this equation, you just click on the equation, and it goes back to the explanation of this equation. Now, this is not the end of it, and I think that we can not only improve the way we can create video lectures, but I think we should also strive to improve the type of video lecture that we're doing. And in particular, current online educational content tends to be a little too rigid. A video is a very linear piece of data. You watch it from the beginning to the end. The navigation that's available is pretty coarse. Also, Rob, for example, has shown some work that makes it a lot easier. And if you compare it to text, when you look at a textbook, it's very easy to quickly look at the titles, decide which equations you want to look at. You can really look at a textbook or an article at different levels of detail. And I think we should try to achieve this with video as well. Some of the work that Rob has shown goes in this direction. The web player that we have also goes in that direction. But I think there's a lot more that we can do. And in general, a theme that many people talk about in education and online education is that students should not be passive, they should be active. And I think really the next step for online content like this is to have students more involved, more active in listening. And for example, one simple thing we can do with something like Pentimento, well, that we will try to do in the future. It's not possible yet, but one thing I really want to do is, say I have that same lecture on the derivation of variance. Some students can decide to listen to it without the visuals, without the strokes, and try to write the equations themselves. And by writing the equations while listening to the audio, they're a lot more engaged in what they're doing, and it's a much more active learning. And the great thing with digital content is that this can be optional. The same video lecture, the student can decide, okay, I'm going to try to do the derivation with only the audio, or I'm going to try to do the derivation without the audio and without the visuals, and it's only if I get in trouble that I'll check the answer. And I think that really digital learning can benefit from this kind of interactivity. So in general, to wrap up, I think that we want to have educational content that's more flexible to watch, that's more interactive, where students are more active. And I think that there are lots of opportunities to invent new types of media that are at the fusion of the notion of slide, the notion of textbook, the notion of video, and that this tablet style is a good place to start because it combines this notion of figure and text with some notion of time that can be optional. And the authoring of such educational content should be a lot more flexible. It should be non-sequential. You should be able to refine your content over time. The next year you want to reuse the same lecture, you should be able to just change that one equation that you didn't get quite correctly in the first place. It should be as easy as editing a piece of text. And I hope also that this flexibility in editing will make it a lot easier to distribute content all over the world, because it will also make it a lot easier to translate from one language to another. And finally, one thing I want to enable is more collaboration between teachers. I should be able to download a lecture that was done by one of my colleagues and adapt it for my class because maybe my students don't have the same background, and I want to add a few notes here and there and say, oh, by the way, when he says this, this is how we've called it in the class, or this should remind you of another lecture that we've done but that this other faculty member hadn't talked about. And so we're interested in systems that make it easier for people to share and collaborate on lectures. Thank you.
Much of the material of education is in the form of either recorded or written natural language, text, speeches, things like that. And it's easy to make the computer search for a simple word and things like that, but if we want more powerful assistance from the computer, we need to have the computer actually be able to understand the meaning of what has been written or what has been spoken. And that requires the application of human language technology. We're very fortunate at CSAIL to have Professor Victor Zhu, who has been a pioneer in the creation of the computer understanding of the computer ability to understand and manipulate human language. Professor Zhu.
Okay, 各位来宾好。So my topic is HLT meets MOOC, and this is the work that I'm doing with a number of my colleagues, and I will identify them as I go along. As Chris said, that we as humans communicate through human language. When I'm talking now, I'm using both spoken and written language to communicate with you. And as a consequence, it is not surprising that human language is an integral part of education. Okay? Whether it's the lecture material, whether it's the books, the textbooks, or the tutorials, or the online discussions we have, we actually use human language. Now, MOOC is an interesting problem. Unlike in resident education, we have a problem, a couple of challenges. The first one is heterogeneity. What it means is that we cannot no longer assume that all the students taking the course are going to have the same background. Sometimes a course, university level course will be taken by students from high school or will be taken by professionals. And as a consequence, their background is different. Some of them speaking English and other people speaking a different language. And their learning style is different. Some people like to read, other people like to listen. So what we want to do is to provide customized learning, to be able to change all those things based on your needs. The problem is that we have hundreds of thousands of students, so you cannot provide only a one-size-fits-all solution. You have to worry about what we call mass customization. You want to enable many people to customize it to their needs. Human language technologies can help, and we can use speech and natural language processing techniques to be able to process and manage the information. We can use it, a speech-based interface, so that people can ask questions verbally, for example, or in writing, and receive answers in the modality that they would like. However, an important problem is because we're dealing with a massive amount of data, these cannot be customized solutions done with human intervention. What we need to do is to come up with automatic solutions whenever possible. So in our group, we're doing a lot of work in this area. For example, how can you transcribe the material? When you see a person speaking, you want to have the transcription perhaps going with it. This is a problem of speech recognition, although in current days, the MOOC courses are typically done by humans, transcribed by humans. Maybe we would like to take the material and turn it into a different language. This is machine translation, but machine translation is a long-term research project. Oftentimes, you like to be able to identify the speaker and authenticate that the person taking the exam is actually the person who registered for the course. And this is very important for security and privacy concerns. And the other problem has to do with information management. What we really want to do is to be able to categorize information. If you have many, many people asking questions, how can you tell that these 547 questions are really asking essentially the same thing? You want to categorize them. You want to link them together so that you want to say, at this moment, I'm looking at a lecture. I want to be able to see the slides, see the person, the transcription, and the lecture notes, and the discussion simultaneously. So you want to be able to link all these material together. And perhaps I want to take a course in biology at MIT, but at the same time, I want to know how the concept is being taught in Coursera at Stanford, for example. And you want to be able to link them from different sources. And you want to be able to summarize a lecture. If I don't have time for an hour lecture, can I get a 20-minute summary or even a 5-minute summary of what the lecture is? And we want to be able to search for information easily using dialogue-based search engines. There are many of these things that I can talk about, but today what I'm going to do is pay attention to this topic of information management. And I'm going to talk about 3 related efforts. And the first one has to do with the following question. Suppose you have a tremendous amount of information, how can I categorize them? I will spend a few minutes on this so that you can take words, phrases, and tag them such that you can look for similar information. And this is the problem of topic modeling. This is the work done by Dr. Liu Jingjing, who has been working with us for a number of years. The second question we want to ask ourselves is, how can we provide a choice of learning path? Remember, I say the background of the students are very different. Some of them may find themselves confused by the current topic. They want to go back and think about some background material first. And still other people might think this is boring. I want to be able to move on to more advanced topic. And this is the problem of learning path discovery. This is done by Dr. Li Hongyi, who received his PhD from NTU, is a visiting scientist working with us at MIT. And the last problem has to do with what I mentioned to you, taking the lecture, the textbook, the notes, and all the discussions of a given topic and try to link them all together so that you can be at the disposal of the person to have sort of very flexible learning. This is the problem of multimedia content linking. This is the work done by Li Shangwen, a second-year graduate student originally from NTU, working with me. So I'm describing these 3 things in terms. The first has to do with the problem of topic modeling. So if I want to know about ethics, for example, and you're going to see many different words that has something to do with ethics. And if I want to know something about disease in biology, I want to be able to think about words and phrases that are related to that. And this is the problem of topic modeling. It's particularly important for a humanities type of course. For example, in a course offered by Harvard called Ancient Greek Heroes, most of the discussion of the material is done online in the discussion forum. So people will pose many different threads of the discussion, and oftentimes you have hundreds of threads of discussion, and it's impossible for a student to look through all those things and try to find the relevant pieces that they like. So what do? They will have to take each one of those threads and somehow find a way to summarize or categorize the topic so that you can say that these are the topics that I like to have. The way to do that is through topic modeling, okay? This is information categorization. So here is a quick way of describing to you what we try to do is to apply a statistical technique to discover the abstract topics. These are not specified by the user. Of course, a lot of the material already have very simple tags, but we want to do much more sophisticated tagging from these material. And the way you do that is a natural language processing technique called latent Dirichlet allocation, or LDA. I don't want to go into the detail, but I can describe to you that if you see these words, milk, meow, or kitten, you say these words are cat-related. And if you have words like puppy, bark, and bone, these are dog-related words. Okay? What we have is a technology that will be able to help you not only group these words together, but generate the right tag for these things. Okay? So you apply this to the problem of information on the online course, and you can find these many different mixtures, and each topic has the probability of generating a certain type of words. And you do this automatically and be able to come up with examples like this. This is for an online biology course. And not only it groups the words that are related to that, and it can create the tag, which is described in yellow here, so that by the time you're done, you arrange the information in such a way that you can find information easily. Of course, this kind of technique is automatic, without human intervention, and you want to be able to train the system for a different course, and then you can apply the same thing. Okay? This is the topic of, this is the discussion on topic modeling. The second topic I want to discuss has to do with how to visualize and infer a different learning path. Different people with different backgrounds, they would like to be able to present or navigate through this information. Rather than going through the detail, I just want to get the gist of the algorithm so you understand step by step what we're doing in this area. The first thing you try to do is data gathering. You want to collect video or the various type of material of many different courses or from electronic textbook online and collect all that information and put it in one place. Okay? The second thing is, what you want to do is to take all these things and try to extract the key concepts. And the way you try to do it, you take the material, providing the transcription, and do some linguistic analysis. For example, you might want to go through a parts of speech tagging, knowing this is an adjective, this is a noun, this is a verb, for example. Then what you want to do is to go through some sort of filtering process and try to come up with words that are important. The way we do that is using a technique called TF-IDF, okay? Term frequency inverse document frequency. This is a way of finding out the important words for a particular document. When you're all done, this is a biology course, you might find these words and phrases automatically. The third step, what you want to do is to find the relationship of all these words and from the transcription. So the transcription say is DNA encodes as DNA encodes RNA. The word DNA and it is a co-reference that we need to resolve. And so you replace that by the word DNA. And then you do some syntactic parsing of that sentence to be able to find the relationship. Here's a parse tree, and it tells you the relationship between DNA and inheritance, which is one is the material of the other. Okay? You can do something like that. Next, what you want to do is to take all that knowledge that you have analyzed and create in what we call a knowledge graph. The nodes of this description in the graph happens to be the key concepts. And the edges that connect the graph basically tell you the relationship among these things. So you can automatically generate these plots and be able to create this knowledge graph. The fifth part is once you have a knowledge graph like this, what you really want to know, which one is the prerequisite, something that you need to understand before you can understand the next topic, for example. In this example, it turns out the word DNA is related to inheritance and RNA. You can see that these words are related. However, if you were to look at the lectures, you would discover that if you look at it, you say the DNA, this word happened in the lecture 3 of the course, whereas the word inheritance is mentioned in the first lecture. So presumably, this is something that you must know before you know this one, for example. On the other hand, if you were to look at the word RNA, for example, DNA mentioned in lecture 3, and RNA is measured in lecture 10. So this must be an advanced concept if you want to move from DNA to RNA. Again, these kind of relationships are inferred by the computer itself. You merge the material together, one course from MIT, for example, another course perhaps from Stanford. And then what you want to do is to be able to link the information together and be able to measure the similarities of the content from the two different courses and link them together if they are similar, okay? If you don't understand the topic that's being taught, then what you want to do is to be able to say, show me what I need to know so that I can understand DNA better. And if you already know about DNA, what you want to do is to say, I want to learn more. And the machine says, the next topic you should study is going to be RNA. So this idea is to provide a navigation for a person to go from one concept to another one, going backwards and forwards, for example. So what I'd like to do is to show you a very short video demonstrating the system that Li Hongyi developed. We call this a system Changjie, and many of you know that Changjie is this mythical person who invented the Chinese characters. And more importantly, this person had 4 eyes, okay? You can see things from all different angles, and that's why we call the system Changjie. Audio?
Massive open online courses to visualize the relationship among many sources of materials. For example, textbooks and lectures from similar courses. By linking these materials together and presenting them in an intuitive interface, Sangqie can potentially help a student customize their learning environment, reviewing background materials or skipping ahead to more advanced topics. The linking and inference is achieved using human language technologies. In this demonstration, a student is interested in learning more about DNA. After a student types DNA into the lookup window, Sangqie returns a biology course from edX and 2 online biology textbooks. It also retrieved a related course on virology from Coursera. A user can retrieve the material by clicking on the color nodes, each representing a lecture in the course or a chapter in a textbook. Through automatic linguistic analyses of the textbook and the transcriptions of the lectures, the system can merge the various sources. The intersections represent points where the materials are similar or related. Note the virology course does not intersect with the other sources, since the material is sufficiently different from the other 3 sources.
Section 2. The structure of DNA.
A student can learn some background material by clicking the Cannot Understand button. The system will then suggest that inheritance is a preceding topic that the student may want to learn first and show the related material. A student can learn more advanced topics by clicking the Learn More button. In this case, Sangqie suggests that RNA may be a topic one can pursue after learning about DNA.
So a person can take all of these material available to you online and be able to create their own learning path to understand the work. The last topic I want to cover has to do with multimedia content linking for MOOC. So we know that lectures, slides, and textbooks and discussion forums of a given topic can play some reinforcing roles. Sometimes you're not so clear on this. You go to check on the discussion forum or look at the textbook, and you want to be able to do that. So what you really want to do is to be able to link the various contents together on a given topic. And what you want to do is to create ultimately an adaptable environment for students to navigate freely. So at any given instant of time, all these things are available to me to study. So the way we do multimedia content linking is, again, just to grossly simplify, what we do is using a modeling technique called hidden Markov modeling. What we try to do is to take the course calendar and try to model the structure of the lectures, okay? And then we try to use the material, both in terms of the transcription and the slides, and try to model the content. And once you have done that, then you can align the textbook sections into the hidden Markov model states. And the linked content are assigned to the same states. So experiments to set up, we did some study on using a Berkeley course on Introduction to Statistics, and we used some video transcription of about 7 hours and slides about 184 pages, and we have a textbook with about 162 sections of this. And we try to evaluate this against labels created by people. 2 different experimenter label the information, and they have pretty good agreement between the 2 of them, over 70% agreement. We try to look at it and say, suppose you only have the video, how well can you do? Suppose you have the video and you know how many pages of the slides are there, how well can you do? And then if you have the transcription of the video plus the slides, all 3 of them. So we use a traditional baseline approach of just counting the word statistics and looking at something called cosine similarity. The second one is the method that we propose using HMM. And the third one is we use the hidden Markov modeling, but we try to emphasize it more by using the keywords a lot more. So the results basically says, if you look at the baseline results, the second column, compare with the third column, you can see that HMM give us much better results, and even better results if you were to use this feature selection process. And the best thing you can do is you can have accuracies of about 66% if you use the video transcription and use the slide, which is good news, right? If you have both of those material, you can do better. So this is a interface of the thing, and the blue one happens to be the video for that particular topic. The red one happens to be the slide, and the green happens to be the textbook. By clicking on any of those things, you can retrieve the information. So in summary, I believe human language technology can help the problem of MOOC in many different ways. And we have achieved some pretty good results at the very beginning on 3 things: topic modeling, and discovering a learning path, and also try to link the contents. Of course, we're continuing to make the system better. We're evaluating the system and moving into as many courses as we can, and many other areas to pursue in this topic. And one of the things that we're hoping, notice that all the people working on this project with me are with Chinese names. And we're hoping that we will be able to collaborate with colleagues in Taiwan to get greater impact. So thank you very much.